And just so I don't forget, we also are when going through the quizzes and to make sure all the grades are added. I should be able to do that by latest on Wednesday, and you should have all the grades so far on the midterm. And I will start assigning midterm grades like this week. So we need to talk about it if you have any question regarding your progress and the situation about the course so far. So these are something we need to go over. Okay. Now, coming back to what we have talked about last lecture, we have gone into share. Now, we need to share first, and we will talk about the one-way slab later. So this week we'll finish here, and then we'll pick up the one-way slab and see if we can finish that by Monday next week or Thursday. Okay. What I want to mention is that for shear, so far, we have mainly talked about 2014 code, that is ACI 3.18.14 version. Okay, now there are reasons for it because most likely you will be using both 14 and 19 design out there. And also in a textbook, the 19 version hasn't arrived yet. Had a brief discussion with professors, writing the textbook, and from what I heard, that he's still delay on that. So we'll probably see it next spring. For all of you right now, we have to take a look at the difference between 2019 and 14, and there is a significant differences. We'll go over them today, and we'll let you know, and you'll see yourself that where we can apply these changes to 14s, or some places we don't have to. Okay, so right in front of me, this is the 2019 code, ACI 3.18 2019. Okay, so it's in the section 22.5.5.5, right? So you can find this from the 14th version as well. Okay, so in contrast of what 14 says, right? So you can see this here. So right now, table 22.5.5.1, this is VC, which is a concrete contribution from non-pre-stressed members. And that's where the main difference is at, only about concrete contribution part, okay? And this is for non-pre-stressed members. This is where we most likely dealing with, right? Non-pre-stressed members. Now, there are two different criteria, as you can see on the left. Is that first AV is bigger than AV minimum. That means when you provide at least minimum amount of shear reinforcement. Now that does not change. Does not change, okay? Minimum amount of reinforcement. Okay, that does not change. Okay, there's a second criterion that we have reinforcement, shear reinforcement lower than the minimum. That means you don't have any shear reinforcement at all, or have very small amount, very small amount. Now, usually we prefer this criterion, okay? Typically, we prefer this criterion. All right, so at least provide something, right? Intersection to resist shear, Okay, now in the design equation, there are two, so you have a choice. You have the upper one and you have the bottom one, right? So the upper one, there's 2 lambda square root f prime c. This is our friend, we have seen this already. And we have additional component that is nu divided by 6 ag. This was also there for 14, I just didn't mention it. This is due to axial forces. Nu is a positive compression or negative for tension, that's for axial forces. That means if I have a member just drawing out here, not only I'm taking care of shear, but also I have axial forces, okay? I have some axial forces. This is what Nu is about, okay? So naturally, if you think of it, what it does is that the compressive stress relieve some of the shear stress on the section, right? So you have helpers from the compression. Okay, so that's the additional part. Now in our design regularly, we don't have any compression forces. Okay, in all the homework, all the exam problem that we have seen and you will be seeing, we usually don't have compression forces. So this part A is not different from what we've been teaching on 14s. Okay, so it's identical on that almost. Now, the main difference is coming from the second category. We have a shear reinforcement that is lower than the minimum. Okay, so what happens is that when you have a lower than minimum shear reinforcement, okay? Lower than minimum shear reinforcement, all right? So your equation changes, So it is no longer 2 lambda, it is no longer 2 lambda squared F prime C BWD anymore, okay? Instead, let me even zoom in so you can see it clearly, okay? Instead, you have this long equation here. You have this long equation here, okay? So let me explain to you what this equation does, okay? So simply, you already know this NU divided by 6AG. This is the contribution from compression force. So I'm just going to say axial compression. Okay, this is from axial compression. So this is same. So the real difference, we're going to use purple color, is right here. This fellow right here. So it changes from 2 lambda square root F prime C to a lambda S lambda and then rho W to the power of 1/3. Okay, so this is a big difference. Okay, so if you're really paying attention, and this is for those of you who want to use the new code, and you probably will 1 year from this time later when you go into the field, that you notice that this is an alternative equation here multiplied by n lambda s, okay, lambda s. So if I want to write down here, so from B to C, so I'll write down here from B to C, okay, so I only change it from 8 lambda rho W 1/3 to a 8 lambda rho W 1/3 multiplied by lambda s. Lambda s. Okay, now this lambda right here, you know it. This is basically 7.5 for lightweight concrete and 1.0 for normal concrete, right? That's just density coefficient. Okay, now the main difference right here is this lambda s here. Sorry, hold on a second. Okay, so the main difference here is this lambda s here.
Professor?
Yes, sir.
I think there might be some people stuck in the waiting room.
I see from where I'm sitting, there are 19 and they're all here already. Is that right?
Okay, I think, yeah, they're in now.
Yeah. Thanks for reminding. Yeah, there was a delay, I believe. Yeah, okay, thank you. Yeah, so let me get this one. Oh, okay. All right, so so the only difference is now that we multiply by lambda s, right? This lambda s is who called the size effect factor, and this is right here. Okay. Now the word is size effect. Okay. So if you look at this equation, all right, this lambda s equal to square root of 2 divided by 1 plus d over 10. And this factor has to be smaller or equal than 1. It's a reduction factor, okay? Now, take a look at this d over 10 business. So as my depth increases, my d over 10 increases. Because it's on the bottom, right, denominator, and then lambda s decreases. So what does it mean is that as the depth of being increases, okay, the shear resistance from concrete, okay, only from concrete, reduces. Okay, reduces. So this is the critical change. That means when you have a deeper beam, your strength reduction factor increases and your concrete strength reduces. Okay, so this is one critical change. This is one critical difference. Okay, so the other critical difference. Now, previously we have in the 14, so in 14, or it stated that the VC shall smaller or equal than 8 lambda square F prime C BWD. And now in 19, 19, it changed to 5. Change to 5. Okay, so this is the main difference. This is the main difference. Okay. All right. So you can see that there are several differences. There are several differences, right? So we have to understand all these, right? The difference between 14 and 19. Difference between 14 and 19. Okay. Now you may say, okay, Bob, so we already went over 14. Now you're saying there's changes on 19. Which version should I go for, right? Which version should I go for? Now in this course so far, and before you go to the job site that requires you to use 19, which will start probably next year, we use the existing design, which are fine. We use the existing design, which are fine. Okay, but if you want to adopt a 19 with the factors, right? Only the cases, let me label this clearly, okay? I have so many labels here, so let me clear this out. The main difference, right? The main difference will be here. When you don't provide any reinforcement at all, when you don't provide any reinforcement at all, now you have to use this 19 code, okay? Now, in our business, right? In our business, we don't see any of this. We don't see any of this. Okay, so far in this course, we're fine. Still use the 2 lambda square root of f prime c. Okay, unless you see this, Okay, all right, so this is so much a difference between 14 and 19. So any questions for me? Guys, any questions for me? Any questions? Are we good? All right, so if you have no question for now, let's move forward. And if you have more questions, we can talk about it, okay? Send me email or can stay behind and we can go over it. Okay. All right. So I hate to be a deal breaker, but just trying to talk about exam real quick. Average of exam is very high. Average of exam is very high. Now, like I said, I don't see any evidence of you guys cross-referencing, cross-checking, collaborating during the exam. I think it's a good sign. And I think the time given that this helps. The exam is designed for 1 hour, but you were given 3 hours, so that's plenty enough time. So I'm happy to see the outcome. Okay, happy to see the outcome. That being said, I noticed some problems. Okay, so some of you, when you do the doubly reinforced sections, some of you when you do the, let me get this to be a smaller font. So for doubly reinforced sections, okay, so for doubly reinforced sections, where you have a compressive reinforcement, right? Where you have compressive reinforcement. Okay, always do a table, right? I shouldn't need to remind you that for the table, there's a compressive zone size. You change it 7, 6, 5, 4 inch, so on and so forth, right? You have compression from steel, compression from concrete, tension from the reinforcement. Okay, now you also have the compressive strain the steel, right? To get you the compression force from steel, that's fine, but you don't have to show it, right? Just for your own sake, all I wanted to see at the end of this table is that you reach CS plus CC equal to T. Now, we said 5% tolerant, right? 3 to 5%. I think the best, let's keep it below 3%. Let's keep it below 3%. Okay, now if you roll 5% your exam, and I accept that, which is fine, but let's get a tighter control on 3%. Okay, tighter control 3%. So this is doubly reinforced section. I see the problem here. Some people just don't like the table. Use the table. Use the table. You can still write your iteration process, all right? But use the table. Use the table. Why? Because this way you can see your process. Okay, you can see your process. So this is one problem I see. Okay, now for the second problem, this is actually on problem 2. Okay, because problem 1, everybody got pretty good. Okay, so I'm not so worried about it. On the second, on the problem 3, what I see is that is design for singularly reinforced section, right? Design for singularly reinforced section. Design for singular reinforced section. Okay, so where I see the problem is that supposedly we gave you a moment chart look like this, and we showed you this is negative 450, 320, whatever it is, and that is negative moment. We mentioned in the problem that is negative bending. Negative bending, okay? So when you do design, always draw the section detail. Draw section detail. Don't forget. So you have a section, right? Draw the bar out. Draw the bar out. Okay. I have a lot of people are so clever. They just draw on the bottom. I say, oh, Bob, in my head, everything's flipped. Well, on site, when engineers, they have to put the bars in, they don't know. They don't know if your head is flipped or not. They don't have time. They probably don't have access to call you, right, to discuss with you where the bars is at, right? They see this and they trust you, trust your stamp. They're going to put a reliability on you if they're dumb, and they're just going to leave the bar like that. Then you have a problem. You have a problem, right? You have a problem. So in a real design, always label the location of bars. Okay, so this is negative bending, so it's going to be on top. Bars on top, bars on top. Now, I didn't take too many points off. If you did everything right in terms of calculation, I know in your head that everything flipped. So I'm trying to be nice here, but this is not a good sign, okay? Now, if I see this again in the following exam, okay, in the second and third exam, there will be no mercy, okay? I cannot give you 3 points anymore. All right, if you draw it wrong, sorry, all points taken off, okay? All points will be taken off. All right, so now these are the two biggest problems I've seen from the exam. Everything else looks fine. And should I remind you of that? In the second exam, we're going to be in person most likely, okay? So be careful. Now, if we're going for in person, you have more nervous breakdown because you work in a room, okay? And although people are so far away from you, like 10 feet, I don't know how we're gonna arrange that, but we'll do that. But you have enormous amount of pressure, okay? So be prepared, All right, okay, good deal. So this is the pass exam. Uh, Final note, I'm very happy about it. I have, few comments on students, some of them. So we have to meet maybe after the class, stay behind so we can have a short discussion. Okay, so today's lecture 15. Lecture 15. So we're continuing the shared design, okay? Shared design. And today we're going to
Hey,
talk
Bob.
about, yes, sir.
Sorry,
Go
I
ahead.
just had to throw my mic on, but will the next exam still be open book, open notes, or will it be different?
If we're going to do in person, probably going to be closed book.
Okay.
So when we say closed book, we're saying like open code ACI and crib sheet.
Gotcha.
Yeah. Okay. So be prepared. All right.
Thank you.
Sure. No problem. So let's go through one example on shear. Okay. Go through one example on shear. Now we had example last lecture. Okay. But that's just a section. So I want you to take a look at the structure level. Okay. So I have a beam, simply supported. Okay, so you can think about it as a bridge or it's a frame. That's fine. So I have a column underneath it like this. Okay, and since simply support, I have loading pads in it. All right, and now let's give some dimensions, right? Give some dimensions. The column here is fixed. Okay, from center to center, okay? From center to center, support is 19 feet. So if I draw it, let me use red so you see it. So this is the center line of the column. Center line of the column, okay? And the distance between the column, 19 feet. Okay, 19 feet. All right, now the distance of a clear span inside the walls is 18 feet. Inside the walls is 18 feet. All right, and the column size, based on this, you probably guessed it by now, the column size is 12 inches, 1 foot. Okay, 12 inches, 1 foot. All right, say I will have distributed load on top of the beam, okay? And I tell you this, now this distributed load here, and you don't even have to compute, right? I tell you this, 9 kips per linear foot. 9 kips per linear foot. Okay, so the question is, right, let's try A, right? VU at center line of support, right? The center line of support, okay? And also at face of the support, face of the support, and at the critical section. What are the critical sections, hey? Think about it, where are they gonna be? And at middle span. Okay, so what are we asking? What are we asking? Right, VU at different locations, so that means I need my shear diagram. I need my shear diagram. All right, so this is asking us to draw the shear diagram. So before I do anything, so I put on my pencil and I do the simply supported condition, which I get the center of the support right here, and the pin right here is a roller. Okay, this is my beam, and then I have a beam sitting on top of it like that. I'm gonna draw my shear diagram. Okay, I'm gonna draw my shear diagram. Move this down a little bit so I have more space. Okay, so what my shear diagram looks like? Time for questions. Time for question. Wake up, ladies and gentlemen. Okay, Wheels Fortune start a turn. Adam.
Yes.
Hello. Hey, how are you doing, man?
Good. How are you?
Not bad, not bad. So here, quick question here. Where would be the maximum shear forces at?
Maximum shear would be the left and the right side.
So the support or the
The
mid
supports,
span?
yes.
Support, great. Good answer. Thanks a lot, Adam. So let me draw the shear diagram just like that. So I have a simply support condition. So the center will be 0. Center will be 0. And the maximum shear is at the support. Maximum shear is at the support. Okay, so I will go ahead and say VU. I know from simply supported beam condition is the omega U multiplied by the length of the beam, right? Divided by 2. Okay, divided by 2. So this right here, VU max, excuse me, equal to the omega U L over 2. Okay, now omega U is 9 kips per linear foot. And the span length is 19 inch. This is from center to center of the support, and divided by 2. Okay, so that is my length, right? That is my length. So just calculate it out. So what I have here, this is 171, and this is divided by 2. So I have, 5.5 kips. Right? So this is my maximum shear, 85.5 kips. Okay. All right. So this is my maximum shear at the center of support. At the center of support. Okay. So go down from here, right? Go down here, and from the maximum shear, I want to find what's the next one is face of the support. Face of the support. So let me just use a different color. I say face of support right here. Face of support is right here. So this is the face of support. VU, let me call it face, right? So for that, how do I get that? I use the linear slope of the shear force, right? So VU at face, right? VU at the face of support divided by length, right? What length? This is the length. So this length right here is 19 feet divided by 2, which is half of the span length, minus this distance, right? This distance is 6 inches, right? So that will be half foot. Sorry, half, 0.15 feet, right? So here, equation become half of L minus 0.5, okay? And that equal to VU at maximum, which is at the end, oh, sorry, center of support divided by L over 2, right? Right, simple as that, simple as that. Okay, so how about this is at face, right? So this is at the center support, this is at face of support. Okay, so let me throw in a number. I'm gonna need some help here, so please prepare your calculator. And this equal to L over 2 minus 0.5 divided by L over 2 multiplied by VU at max. So VU at face of the support equal to, this is 19 divided by 2 minus 0.5 divided by 19 divided by 2 multiplied by 85.5 kips. All right, I need some help to check my number. Benjamin, Mr. Wood, are you there?
Yeah, what's up?
Hey, can you help me out? Get a number for me, please. Simple calculation. Do you have a calculator by your side?
It's 81.
81. All right, good deal. Okay, makes sense. Thanks a lot. So that's the shear force at the face of support. At the face of support. So going down here, right? This next question is, what is the shear force at critical section? Critical section. Now, where is this critical section is going to be at, right? Where this critical section is going to be at? So we said, right, the critical section is going to be what? Is going to be the D depths away, D away. So let me just take this one out so you see it better. So D away from the face of the support. D away from the face of support. So this is the critical section. So VU at critical section. Okay, and what is the depth of beam? What is the depth beam? We don't know. We don't know, right? I have no idea what is the depth of beam. Okay, so let me see, right? Let me see that. I'm gonna throw in some number in. So I say, look, I'm gonna say the depth of beam equal to 24 inches. All right, 24 inches. So at the critical section here, VU, go back to this color, VU at critical equal to, use the same triangular, right? Same triangle. So it's going to be L divided by 2 minus 0.5 feet. That's the face of support, minus D, depth of beam, divided by L over 2. Okay, and this must be VU max. Okay, VU max. All right, so put the number in. So this is going to be 19, okay, 19 feet divided by 2 minus 0.5 feet minus 24 inches, 2 feet, divided by over 2. So it's 19 divided by 2. All right, need help again. You find some numbers from here. And this is multiplied by 85.5 kips. It's on my list. Austin, are you there?
Yeah, I'm here.
Hey, can you help me out? Get a number for me?
Yep, I'm putting it into my calculator.
Oh, no worries. So it's 19 divided by 2. So I figure this is 9.5 minus 0.5 and 9 is 7 feet. This is 9.5. Yeah, what you got?
63.
63, right?
Yeah.
Okay. Yeah. Thanks. All right. So I got all these shear forces.
Question.
Yes, sir.
Was the 2 given earlier or did I just miss it?
No, I just give something randomly right now.
Okay. So
Yeah.
it would be given another question.
No, we will give you at the time for homework and exam, right? You have to know the depths of beam. Okay. All right. Okay. So this is all the shear I need for the section, right? So now I have a shear diagram. I have a complete shear diagram. Okay. So let me draw it out, right? So at this point, I say, oh, look, I have a good shear diagram. So my shear diagram looks like this. Since it's symmetric, since it is symmetric. Why? Because I know this is 0. in the middle span, and the other side looks just like that, but flipped, right? So I'm gonna use half span. Okay, I'm gonna only use the half span. And look at the triangle here. Look at the triangle here. Okay, and that's the 0 shear. Okay, so I'm gonna start drawing my distance. I'm gonna start drawing my distance. Okay, so now first distance, right? Let me draw it far away. So let's see how many I have. So I have here. This is VU max at the center of support. Okay, sorry. Let me get this to be bigger. So I want to exaggerate a little bit. Okay, now these dimensions are not proportional, so I can exaggerate a little bit. Okay, I want to exaggerate a little bit. So this is VU at face of support. Okay, and this is VU at critical section. Critical section. Okay, and we have all these numbers now. This is 63 kips. And this is, I believe, let me see here, 81. And that is 85.5 kips. Okay, and not only that, we have distance. We have distance, right? So this distance right here is 7 feet. Okay, and this distance right here from face of the support, okay, is 9 feet. And this distance right here is 9.5 feet. Okay, now this is the complete shear diagram. Complete shear diagram. All right, so how are we going to design for shear? How are we going to design for shear? Okay, so let's say now I want you to design, this is shear diagram. I want you to design this beam, design shear or web reinforcement. Okay, for a T section, that looks just like this. Okay, looks just like this. And I say the depth of the beam is 24 inches. Okay, and concrete cover is 3 inches. So H height of the beam equal to 27 inches. Okay, I have a flange width of 36 inch, height of 3 inches. Okay, and I have my web is 12 inches. Okay, this is the cross section. This is the cross section. All right, so the question is designed for shear. All right, I already have fletcher. So don't have to worry about that. Don't have to worry about that. Okay, all I have to do is check for my shear. Check for my shear. So how do I do that? How do I do that? Okay, so first thing first, right? I have to give you the properties, right? Also, F prime C equal to 4 KSI. And the stirrups I'm going to use have a 60 KSI yield strength. 60 KSI yield strength. Okay, so if I do this, right? If I do this, first thing I need to do is do what? I need to find my concrete contribution. All right, so to design, I need to have my VC, which is the concrete contribution. And we go with the minimum. So if AV mean is provided, okay, if AV mean is provided, we use VC equal to 2 lambda square root of F prime C BWD. Right? So 2 lambda, the normal way concrete, so lambda equal to 1, so this becomes 2, and this is 4,000 inside. And be careful, I need some help again. This is 12 inch of B web, all right? This is 12 inch, okay? And depth is 24 inches. 24 inches. Brett, hello, are you there?
Yep.
Hey, can you help me out here? Can I get a number on this?
Putting in right now.
Sure. 2 square root of 4,000, 12 inch, 24, what you got?
36,429.4.
So can you convert the kips 2,000 pounds. So it would be 30.
35.
30. So 33.5 or 30. 35. Which one?
Dividing by 12,000, right?
This
12.
is already inches, right? And this is PSI, right? All you have to get is kips, right? So you don't have to divide by 12,000. You only divide it by 1,000, isn't it?
Oh, yeah, my bad.
No worries. Can you do it again?
36.43.
Okay. Good. Okay. So this is the VC. This is VC. So phi, and where I'm having you here, Brett, don't go yet. So phi VC 0.75 multiplied by 36.43 kips. What do I get?
27.32.
27.32 kips. Wonderful. Thanks. That checks out. Okay. So that's phi VC. All right. That's phi VC. So first of all, if I have phi VC 27.32, and looking back at the shear diagram, right? This number, right, about 27.32, probably somewhere here. Okay, somewhere here. Okay, now I know for a fact that shear on the right-hand side of this line here, right, is smaller than phi VC. So most likely I don't need to have design stirrups. Okay, I don't need design stirrups. And to be even better, I know that if I take half of phi VC, right, which is about 13 kips. Okay, 13 kips. I know that from this line forward, I don't have to do anything at all. I just need to provide a minimum reinforcement. Okay, minimum reinforcement, right? So now I can start envision things. Before I even get into calculation, I can start envision things, right? So before I do that, let me find a distance first. Right? I just want to find out, I'm going to use red here because these are a little bit different. I just want to find out what is the distance between the center span to my phi VC here, and what is the distance between half of phi VC to my middle span here. Okay, so to do that, I just need to do a calculation, right? So phi VC, okay, and say I have a distance and set it equal to x1, and this is x2. Okay, so phi VC is red here, so you see it where it corresponds to. So phi VC divided by distance x1 should equal to previous calculation, which is 63 kips right here, corresponding to 7 feet. Okay, should equal to 63. So VU critical divided by 7 feet. Okay, so the distance x1 here would equal to phi VC 7 feet divided by VU critical. Okay, and that is 27.32 kips divided by 63 kips multiplied by 7 feet. I need help again. Bryce.
3.04.
So 3 feet.
Yep.
All right, good deal. Thanks a lot. So where I'm having you here, Bryce, don't go yet. Bryce, don't go yet. So if I'm going to use half of that, so half phi VC divided by x2 VU critical, same 7 feet. So x2 equal to half of this. What do I get, Bryce?
1.5.
Right. So 1.5. Right. Great. Thanks a lot. Okay. Very simple calculation. So I have 1.5 feet. All right. So these are distance. With this, I have an updated shear. I have an updated shear diagram. So to help you out, I'm just gonna cross this whole thing and copy paste it again, copy it and paste it again. So now I have the complete picture. I have a complete picture. Okay. Okay, so I have a complete picture. So now let me even move this further. Okay, let me move the 7 feet a little bit lower here. Put this 9 feet a little bit lower here, 9.5 feet, even lower here. Okay, so finish this shear diagram, right? So I have this shear diagram, and then I have now this is 1.5 feet, 1.5 feet, and this is 3 feet. Okay, now I'm done. I'm done. So this is the full shear diagram. I'm not done with design yet, apparently, but this is my full shear diagram. Okay, so I look at this, right? Why I'm using FVC, half FVC? Because I know eventually I'm going to compare my contribution from concrete to my applied shear, to know which region I'm designing for, So I just label this. So where I'm having it, right? Where I'm having this, right? So I will continue to look at how about my 4 lambda square root f prime c BWD, where that is at. Okay, and proceed. Now you know it can now be bigger than 5 times square root f prime c BWD for ACI 19. Okay, so where these two are at, Okay, so if I have these two numbers, right? If I have these two numbers, I don't know exactly where they're at. But I'm just gonna draw them out, right? Assuming they're gonna be something like here. Oh. Assuming that this is bad drawing. Let me connect this. Now these are some of my shear lines. Okay, and assume that my 4 lambda square root f prime c is here. And assume my 5 lambda square root of prime c BWD is here, then I can have zones. Essentially, okay, I'm just gonna do a spoiler here. Essentially, lower than this number right here, this region here, let me label 1, stirrups free, or at least provide some minimum. Okay, and this, in this region here, where it is between half of VVC and VVC, we need to provide stirrups as well, right? AV mean, and also maximum spacing applied. Maximum spacing start apply. Okay. Now between 4 lambda square root of prime c and this right here is region 3. Okay, region 3, we have to calculate the spacing from the stirrups. Okay, we have to calculate the spacing from the stirrups, right? Using that equation for stirrups. And then beyond this, we need to have halved spacing, halved of 3. Now, if there's any applied shear that is even beyond 5 lambda square root of prime c, and I call it region 5, this is need to change section size. Okay, need to change section size. So this is our game plan. Okay, and that's why we spend so much time in calculating the shear at different locations and also concrete contributions on the shear diagram. And we'll proceed to calculate 4 lambda and 5 lambda in our next lecture. Okay, we'll proceed to calculate this in our next lecture. All right, okay. So this is halfway. I want to stop here so we continue to pick up on Wednesday. Any questions on this? Folks, any questions on this? All right. We will not leave the shear homework until Wednesday. So we'll probably will have a delayed shear homework starting the Thursday. Okay. Now Monday is homework number 6 due date. There was a postponement, And some of you receive a late score and some their communication problem with the TA. So I sorted out today with him, but submit homework number 6 today, okay? All right, any other questions for me?
I've got a question about the homework, if I
Yes,
could
sir.
ask you.
Yes, sir, go ahead.
So